Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we will talk about alkanes. We'll discuss its physical properties very briefly. And then we're going to talk about what it is and how to name them. So let's go ahead and start. So the word alkane is a general term that organic chemists kind of like toss around to describe organic compounds in which the bonding between the carbon atoms are only connected by a single bond. And so you're going to see a variation of the root word alk, right? So you can have an alkane, an alkene, an alkyne. So if it is an alkane with a suffix of ane, then the bonding between the carbon atoms in the parent chain, and we'll talk about what the parent chain is in just a second, if the bonding is only a single bond in the parent chain, then that organic compound can be classified as an alkane. Okay? And so all alkanes exhibit this sort of physical property where they are non-polar in nature. In other words, they are immiscible or they do not, they're insoluble in water. And so if you were to put an alkane in with water, you guys are going to create a heterogeneous solution. And since the density of an alkane is typically lower to that of water, that means that if you were to mix an alkane with water, you guys are going to see a separation between the two, such that the top layer of your solution is going to represent the alkane, and the bottom layer is going to be water. So if you guys can just like imagine putting oil and water together, oil floats on top because it's less dense. The same thing occurs for alkane. And so if you are an organic chemist or a budding organic chemist, you can probably use these physical properties to separate out substances. And so they also have a low boiling point. And so if water boils at 100 degrees Celsius, since water boils at 100 degrees Celsius at 1 atmospheric pressure, if you have a mixture of an alkane and water, you guys can boil it, and the item that evaporates first will be the alkane if it's less than 100 degrees Celsius at 1 atmospheric pressure. So you can perform like a separation between the two substances based on their boiling points. Now, alkanes that are acyclic. So acyclic means it's not a ring. And if it's not a ring, then it is considered a chain. Okay. So if your alkane is a chain, then the general formula to describe an alkane is going to be this: CnH2n plus 2, where N represents the number of carbons. Okay. And so this formula can help us predict or identify whether or not a substance with a given chemical formula is an alkane, an alkene, or an alkyne. So if we were to look through an example, let's just say that we have this organic compound. So if you guys recall, each point on this zigzag line that I just drew represents one carbon. And so if this is a 5-carbon compound, then the value of N is equal to 5. And so if you guys are plugging it into the formula, I'll just work up here just for a second. We have C5H2 times 5 plus 2. Okay. So that's where the N is coming from. We're just putting in the value of N in this formula. And so if you have a 5-carbon organic compound with no heteroatoms, and it's not a cyclic molecule, then the chemical formula is going to be C5H12. Okay. And so this is the chemical formula for pentane. And so since we have the full amount of hydrogens per carbon in the chain, acyclic alkanes are also considered saturated alkanes. So remember that carbons wants to have 4 bonds. Okay? They want to achieve that octet rule. The number of bonds can be represented by a double bond, triple bond, or a single bond, or any combinations, just as long as there's 4. And so if you guys are looking at this carbon, which represents this ball and stick model, notice that it has, I'm going to zoom in here, it has 1, 2, 3, and then 4 at the very back. So it has 4 covalent bonds, and of those 4, 1 is actually required to be covalently bonded to another carbon. And so the potential, the maximum number of bonds that carbon can have to a hydrogen is 3, okay, given its current scenario. And so we would say that carbon is saturated with hydrogen. Now, if you look at the second carbon, notice that it's obligated to, maybe I should do this in a different color. The second carbon is obligated to have 2 bonds dedicated to carbon, so the maximum number of hydrogens this second carbon can ever have is 2. Okay? And so given its scenario, it is considered to be saturated as well. Okay? Now, if it is unsaturated, that means one of these hydrogens was no longer present. And for instance, like a heteroatom, such as like a nitrogen or oxygen, can take its place. And so if a heteroatom takes its place, or if there's like a double bond or a triple bond or something like that, then that carbon is unsaturated. So we can kind of go through that logic for every single carbon that you guys see here, and you'll find that given the number of obligated bonds it has to other carbons, each carbon has the maximum number of hydrogen atoms that it can attach to, given its condition. And so we would say that this alkane is saturated with hydrogens. Okay. Now, earlier I mentioned that these alkanes are nonpolar. And so if you guys recall from general chemistry, polarity can be described in a couple ways. I think we kind of agreed to, for the sake of this course, that we're going to determine polarity based on the presence of the lone pair on the central atom and the symmetry of the peripheral atoms that's on that central atom. And so if you guys look at this carbon right here, notice that everything is, like carbons and hydrogens. And carbon, that's a non-polar covalent bond. I think I really should do this in a different color. So this bond right here, carbon to carbon, if you calculate the change in electronegativity, its change of electronegativity is 0 because it's the same element. It's carbon and carbon. Now, if you calculate the electronegativity, the difference in electronegativity between carbons and hydrogens, they will fall under the nonpolar covalent range. And so overall, this molecule exhibits a nonpolar character to it, just because there's no lone pairs present on the central carbons, and everything else is pretty much symmetrical, right? We all have hydrogens, and the type of bond between carbon and hydrogen is nonpolar covalent bond. Okay. And so that's what gives it, its physical properties. For example, it's nonpolar when you try to mix it with water, it'll separate. Okay. All right, so we're going to talk about the IUPAC naming for the first 10 alkanes. This is something that you guys should really memorize, just because we're going to be using like the prefix that you guys see here, and you guys will you will see very soon that these prefixes and the base name will help us build on how to name the compound of a random alkane organic structure. Okay, so let's go ahead and go through the motions. So on the far left side of this table, 11.2, these numbers that you guys see here represents the number of carbon atoms that's inside the organic compound. And so, for example, if you only have one carbon, an example of a saturated alkane, actually the only example for a saturated alkane with one carbon is CH4. Now, the name of CH4 is methane. So I'm sure you guys have heard of this before. Actually, maybe you've heard of the first four: methane, ethane, propane, and that's the same propane that you guys are using for barbecue, and butane, like the fluid that's in the lighter. And so where these names come from is from the combination of two sources. One, the prefix. So from here on out, if there is only one carbon, the prefix is meth. Okay. And so, for example, if you have two carbons, the prefix is eth. If you have three carbons, the prefix is prop. And then if you have four, then that's bute. Number 5, pent. Number 6, hex. Hex. Number 7, hept. Number 8, oct. Number 9, non. Number 10, dec. Okay. And so once you guys have memorized the name of the prefix to the number of carbon atoms, then all you're going to do is attach the suffix. Now remember, this is all single bonds, like the carbon to carbon. So like this right here. Oops. Let me change my color real quick. So the bonding between carbon to carbon is a single bond. Okay. And so since the bonding to the carbon is a single bond, then we're going to use the suffix ane. Okay. And so if we add the prefix, whatever the prefix is, depending on the number of carbons, plus ane, you get the full name of that organic compound. So methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. Okay. And so to obtain the chemical formula, you guys can go ahead and use the equation CnH 2 times N. So remember, N is representative of the number of carbon atoms. So for example, if we have, I don't know, nonane has 9 carbon atoms. And so if we have 9 carbon atoms, then the number of hydrogen atoms that we'll have for it to be saturated is going to be 2 times 9 plus 2. So if you reduce this, 2 times 9 is 18. 18 plus 2 is 20. And so the chemical formula for nonane is going to be C9H20, which is what we find here. Okay. So hopefully you guys understand how the molecular formula could be derived simply by knowing the number of carbon atoms in your organic structure, as well as its general name. Now, if you guys are looking at the condensed structure formula, so here this is, they're showing you the connections between the two. So the idea is that you have your CH3s grouped with your, grouped on its own, and it's separated from the next carbon, etc., etc. So for the structural formula, you guys can kind of count the number of carbons and how the hydrogens are distributed for each value. So if you look at methane, methane has 1 carbon. And if there's only 1 carbon, then there must be 4 hydrogens, right? So this, if you guys are looking at ethane, it has 2 carbons. And then if you guys have propane, you have 3 carbons, and so forth and so forth and so forth. All right, and so how do we depict the skeletal structure of these condensed structural formulas? Now remember, the skeletal structure is the squiggly lines, like all of this stuff, where each vertice is representative of a carbon that's either in your condensed structural formula or your expanded structure. Now when you guys are writing the skeletal structure for methane, you guys just have to write it as is. I mean, technically speaking, for it to follow the rules to the T, then like a dot would represent methane. But at this moment in time, you guys can just write methane on its own, CH4. For ethane, since there's 2 carbons, the skeletal structure is going to look like this. For propane, which is 3 carbons, the skeletal structure looks like this. For butane, it's 1, 2, 3. So that's 1, 2, 3, 4. For pentane, we have 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5. Okay. So pentane is kind of like an M, right? Or I don't know, like Mario, and if you flip it upside down, Wario, or W. And so both of them are equivalent. You don't actually need to start from the bottom, you can start from the top. So for this one, you guys can start from the top, and it'll still be representative of butane. Same idea here. I can do a V instead of that caret sign. All right, so for the next compounds, we have 1, 2, 3, 4, 5, 6. 6 is hex or hexagon, right? And since they're all single bonds, so if you look at the bonding between each carbon, it's all single bonds. So therefore, I need to use the suffix ane. So therefore, the name is hexane. And so to draw the skeletal structure, I need 1, 2, 3, 4, 5, 6. Okay. or 1, 2, 3, 4, 5, and 6. So 1, 2, 3, 4, 5, 6. So don't be afraid to double check your work by kind of putting those dots on either the corners or the vertices where two lines meet, or at the end of the structure. So for the next one is heptane. So that's 7 carbons. So that's 1, 2, 3, 4, 5, 6, 7. Octane, 1, 2, 3, 4, 5, 6, 7, 8. Okay. And hopefully you guys get the pattern for 9 and 10. All right. So please make sure that you guys memorize this. I know that we're doing distance learning. However, it's really, really important to have the prefix and the suffix memorized, just so when you're applying this to naming a more complex organic compound, you're not scrambling through your notes. Okay. So let's go ahead and talk about the conformations and the rotations of alkanes. And so I kind of alluded to this in the previous video. So if you guys can imagine a pencil, right? So imagine that you have a pencil or a toothpick and you just have one of it. And you stick like a marshmallow. You stick 2 marshmallows of different colors on both ends of the pencil or the toothpick. And so if you imagine that this part of the molecule is like one marshmallow and this part of the molecule is another marshmallow, could you rotate those 2 marshmallows around the toothpick or the pen with very little movement? Okay. And the answer is yes. And so for alkanes, the really cool thing about alkanes is that since it's a single bond, the bond can rotate 360 degrees. So the rotation can go up to 360 degrees. Okay, and so that's a feature that's a feature that's commonly found for single bonds. Now, sometimes, depending on the bulkiness of your organic compound, sometimes, if you have a single bond, it's not a full 360 just because there's something called steric strain. And so if you look at butane right here, this is actually the preferred arrangement of butane. Now, if you guys rotate this molecule such that this piece or this end is flipped over to this side, so that's 180 degrees rotation, then you get a structure that looks like this. And notice that there's some crowding between these 2 bulky methyl groups. And so this crowding prevents this molecule from, rotating it always to this specific conformation. So your alkanes are always rotating, but if there's some crowding, it doesn't want to conform to that specific orientation. So it's just going to move away from that. So in theory, your alkanes can move 360 degrees. However, if there's some bulky structures that's attached to 2 of these alkanes or 2 of these carbons that you're trying to rotate, then it might not conform to that specific orientation, and another orientation might be favored. Okay. All right, so let's go ahead and name and draw the skeletal structure for these compounds. And so if you guys are looking at the first one on the left, this is the expanded structure. And so if you guys remember from general chemistry, if you have a bold line that represents that this hydrogen or this substance is out of plane and pointing towards you, right? So, for example, if you guys take your pencil or your pen and move the pencil or pen such that the cap or the eraser is pointing at you directly, then that is what that bold line is representing. So the tip end of your cap of your pen or the eraser part of your pencil is going to represent the hydrogen. The middle of your pencil is going to represent this carbon. And so the dashed line is going to represent the tip end of your pen or pencil in the specific orientation that I had you guys, that I had described. Anyways, I digress. So let's go ahead and talk about the name and the skeletal structure for this compound. So notice that there are specifically 2 carbons. And so since there are 2 carbons in this chain, we know that that prefix is eth. And since it's a single bond, then we know that we're going to use ane as our ending. So together, this is eth-ane. Okay? So hopefully that made sense. So I'll put single bond here. Equals ane. All right. So let's go ahead and look at this example. How many carbons do we have? We have 1, 2, 3. And if you look at the connection between all 3 carbons, they're all single bonds. So once again, that informs us that we can use the suffix ane. And since we have 3 carbons, that means that the prefix is going to be prop. And so if you put this together, we get propane. Okay. Now, if you look at this structure, it's depicted a little bit differently than the second example. However, if you look at the number of carbons, 1, 2, 3, and if you look at the bonding between the carbons, it's still a single bond. And so therefore, this structure is still considered to be propane. Okay. So I use these 2 examples to highlight that the molecules can be represented in different ways. And so in the way on the left-hand side with the bold and the dashed, it's showing like the 3-dimensional geometry of this specific organic compound. Whereas if you look at the structure on the right, where there are no bold or dashed lines, and they're all, normal lines, so this is the expanded structure, that is also describing propane. Okay. And so let's go ahead and look at a couple more examples. We were supposed to draw the skeletal structure for these 2. So very quickly, to draw the skeletal structure for ethane, 2 carbons, just 1 line, we're done. Here for propane, notice how there's a line here and a line there. I'll go ahead and zoom in. And maybe this will clear up the confusion, if there's any confusion on how to draw a skeletal structure. Notice that there's a line here and there's a line there. So we're going to only represent those 2 lines in our skeletal structure. And so I'm going to connect those 2. So I have something that looks like this. So this is propane. Okay. So same thing here. I have 1 and 2 bonds between the 3 carbons, which is going to be my parent chain. And so I'm going to draw propane that looks like this. Okay. And so once again, these molecules are three-dimensional. And so you can go ahead and depict your skeletal structure in many different perspectives and many different ways. The only way that your skeletal structure can be wrong is if you do not put in the correct number of carbons, or you guys don't have the correct number of vertices, and the bonding is incorrect, or the number of heteroatoms that's found is incorrect. Okay? So you always want to double check to make sure that your skeletal structure truly does reflect your expanded structure, and so forth and so forth. But hopefully through, by looking at this image, you can see that there are 3 invisible hydrogens for this carbon. Okay, and there are 2 invisible hydrogens on this carbon, and there's 3 invisible hydrogens on the last carbon. Okay. Same can be said with the other propane. All right, so let's go ahead and name and draw the skeletal structures. Here it's given to us in our condensed structure. So notice how all of the single bonds were taken away and we're just left with carbons and hydrogens. And so to figure out the name of this compound, we're just going to simply count the number of hydrogens, or carbons, sorry. So 1, 2, 3, 4, 5, 6, 7 carbons. And I don't see any double bonds, because remember in the condensed structure, you have to show double and you have to show triple bonds. And so if it's not shown, then everything is a single bond. And so I know that I'm going to be using my ANE ending. And since I have 7 carbons, that invites me to think of the prefix hept. And so you guys put them together and you get heptane. Okay. And so to draw the skeletal structure for heptane, we just want 7 points. So 1, the moment you put your pencil or your pen down, that's carbon 1. 2, 3, 4, 5, 6, 7. Okay. So hopefully you guys got that. All right, so same idea for this example. We're just going to count the number of carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so if we have 9 carbons, the prefix is going to be non. And then since there are no double bonds or triple bonds, then we're going to add ane. So overall, the name of this structure is nonane. So now that we figured out this is nonane, we're just going to go ahead and draw the skeletal structure. So starting with carbon 1, so the moment you put your pen or pencil down, that is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. And this is going to be the structure for nonane. So last but not least, we have 1, 2, 3, 4, 5, 6. And so 6 carbons represents the prefix hex. And once again, I don't see any double bonds or triple bonds, so I'm going to use the suffix ane. And so the name of this compound is hexane. And when I'm drawing my Lewis structure, not my Lewis structure, my skeletal structure, the moment I put my pen or pencil down, that's carbon 1, 2, 3, 4, 5, 6. Okay. Or if you started from the top, you'll go 1, and then this is 2, 3, 4, 5, 6. Okay. So both are equivalent. You can start at the top, you can start at the bottom. If you want to be a radical and do it from the side, you guys can. Just make sure that there's the correct number of vertices to represent the number of carbons. All right, so that is acyclic alkanes. And so if something is acyclic, that means it's not a cyclic ring. That also implies that there are compounds out there, some alkanes that are cyclic, that are in a ring. And so they are known as cycloalkanes. And so cycloalkanes are alkanes that form a ring. And the one thing that you guys should know, another stark difference between cycloalkanes and alkanes is that they are unsaturated. And so if you guys count the number of carbons, 1, 2, 3, 4, 5, 6, if it's saturated, then a 6-carbon compound should have a chemical formula of C6H 2 times 6 plus 2. Right, so where that 6 is representing the value for N. And so when you add all of this up and multiply it, you get C6H14. And so that is if this compound is saturated with hydrogens. Now, if you look at the acyclic form, so here it's just kind of drawn for us. So this is cyclohexane. The black spheres represents the carbons. So we still have 6 carbons. But if you count the number of hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 hydrogens for this cyclohexane, which is a cyclic alkane. Now, if you guys look at the theoretical amount, for a saturated compound, it's supposed to be C6H14, but that is not what we're getting here. And so this tells us that cyclic alkanes are unsaturated. Okay? And mathematically, they go by the chemical formula CnH2n. Okay, so this is the formula for cyclic alkanes. Or cycloalkanes. And once again, you guys can plug in any carbon number, and you guys should be able to predict the number of hydrogens, and that's going to represent the chemical formula for that organic compound. And so I kind of jumped ahead, but let me go ahead and erase all of this stuff here. And so whenever you guys are drawing cyclic alkanes, once again, the corners, I'll go ahead and put this in red. So these corners in the ring is representing a carbon. And anything that is not shown, if you guys recall, represents a hydrogen. And so if I erase all of this stuff that I kind of circled, notice that if I label this as carbon 1, just arbitrarily, that's going to represent this carbon, carbon 1. And carbon 1 has 1, 2 hydrogens attached to it. And so we have to remember that there are 2 hydrogens that's not shown in this skeletal structure. Okay. And so if you were to think about the number of invisible hydrogens that's omitted for this skeletal structure, for the rest of these vertices, there should be 2 hydrogens. And you guys can see that by looking at the picture on the right. Okay, so every single carbon has 2 hydrogens. However, when we're writing it in the skeletal structure format, we ignore all of those hydrogens. And when we're ignoring all those hydrogens, the only thing that we have left over is just the black spheres. Okay. All right, so let's go ahead and talk about the possible cycloalkanes. Like, what is the minimum number that you need to have of carbons that'll enable you to produce a cycloalkane? Okay. And let's go ahead and start with carbon 1. And so, could you have a ring? Can you form a ring with 1 carbon? The answer is no. Okay? And so if you have 1 carbon, there's no possible way for you to have a cyclic ring of just 1 carbon. So no cyclic version is possible. Let's think about carbon 2, or I'm sorry, 2 carbons. If a compound has 2 carbons, could you ever put them in a specific orientation such that they will form a ring? Okay. The answer is no. And so I'm going to go ahead and repeat. And you can kind of think about it for yourself. Remember, carbon, just like 1 dot. 1 carbon is 1 dot. 2 carbons are 2 dots. There's no way that you can have a ring, you can form a ring with 2 dots or 1 dots. Now for 3 carbons, right, is there a way for you to arrange 3 carbons or 3 dots such that you can form some type of ring? And this isn't like the ring that we think about in our finger, just something that is cyclic or enclosed. The answer is yes. A cyclic version is possible. Okay. And so what does it look like? Well, it's a triangle. Okay. And so here I have 3 carbons or 3 dots, and connecting them will form a triangle. And so the name is going to be cyclopropane. So notice that I'm using this word propane to represent 3 carbons, and actually let me take it back here. Okay. So this word prop tells me that there's 3 carbons. This suffix ane is telling me that they're single bonds. And this addition of cyclo tells me that it's going to be enclosed. Okay. And so therefore, the name of this structure is cyclopropane. Now, we can go through this exercise for the rest of them, but if you have like 4 carbons or 4 vertices, 5 vertices, 5 carbons, 6 carbons, 6 vertices, and the list kind of goes on. Could you create some type of enclosed or cyclic structure out of them? And so the answer to that is yes. So after you guys, if you have greater than 3 carbons, then there is a possibility where you can create some type of cyclic compound with that specific number of carbon atoms. And so just to demonstrate a few, at some point it's going to get really hard to draw. So 4, we can have a square. And the name of this square is going to be cyclobutane. So it's a ring, so that's where the cyclo comes in. There's 4 carbons, that's where the bute comes in. And the connection is all single bonds. And so that's where the ANE comes in. All right, so let's go ahead and do the next one. 5 carbons. And so could you guys think of a shape that has 5 vertices? And so if you guys thought about a pentagon, such as the one in the East Coast, you're absolutely correct. So here I have 1, 2, 3, 4, 5. And so the name of this organic compound is going to be cyclopentane. All I'm doing is I'm adding the word cyclo to the parent name that represents 5 carbons, and all of the bonds are single bonds. Pentane. And so if you guys think about 6, 7, 8, 9, 10, those are more complex structures to draw. And I'll probably only be able to draw maybe up to 8, who knows. And so for 6, it's going to be cyclohexane. What do you think the name of the rings are for 7, 8, 9, 10? Okay. And so for number 7, it's going to be cycloheptane. For number 8, it's going to be cyclooctane. And so there are 2 consecutive vowels. However, in terms of the enunciation, they're like the syllables, they're separated. So it's cyclooctane, right? And so you guys cannot combine those 2 O's together like what we did when it came to naming inorganic compounds. And so for number 9, hopefully you guys understand the pattern. This is going to be cyclononane. Number 10, cyclodecane. Okay. And so this is really important for you guys to know your roots, right? Know what these numerical prefixes mean. Hex, hept, oct, non, dec, bute, eth, meth, and prop for organic chemistry. And so for cyclohexane, here we just have, we actually saw an example of it in the previous slide. Okay. So notice that there are 1, 2, 3, 4, 5, 6. And so cycloheptane, I always have a hard time drawing this one. Let's see if I can get it in one shot. So, 1, 2, 3, 4. Did I do it? 1, 2, 3, 4, 5, 6, 7. Yay, I did it. All right, so cyclooctane, that's actually going to be like your stop sign. So if you guys can draw a stop sign, then you guys are looking good. Okay. Let me redraw that. I think the first one was better. Anyways, and so as you can see, as you add more and more vertices, 1, 2, 3, 4, 5, 6, 7, 8, it's gonna start looking like a circle if you draw it like very small. But if I were to kind of draw it larger, I shouldn't have that issue. Okay. All right, so that's our cyclooctane. And you guys get it for cyclononane and cyclodecane. I'm not going to draw those structures. And so these are all of the possible cyclic compounds or cyclic alkanes, I apologize. So it's going to start off with cyclopropane. Okay, so anything 3 and up, a cyclic version of that alkane is possible. Okay. All right, so what we're going to do is we're going to get some practice naming this. So here, when you guys are given this format, you guys are just going to count the number of black spheres, because remember the black spheres represents the carbon in your ball and stick model. And so if you look at the black spheres, there's 5, and it's a cyclic ring. So this is cyclopentane. If you guys are looking at the next example, how many black spheres do you see? There's 6, and they're all in a ring. So this is going to be cyclohexane. So for the last 2, there's 3 carbons, but it's in a ring, so it's cyclopropane. And last but not least, here we see 4 carbon. It's like a square, so it's 4 carbons, so it's going to be cyclobutane, because there's 4 carbons. Okay. All right, so hopefully you guys have a handle or understand how to name these very simple organic compounds. And so, I mean, if this was organic chemistry, then we would be done with this semester, and that would be it. But unfortunately, these organic compounds can be very, very complex. And so, in the next video, we'll talk about substituted, or we'll talk about alkanes with substituents. All right. I'll see you guys in the next lecture video. Bye.